Hello students, this is the second part of the Chapter 5 material. In the first part of Chapter 5, I talked about two reaction types that you're going to be responsible for knowing and recognizing and knowing how to analyze. And those were precipitation reactions and acid-base reactions. In this video, I'm going to be completing this reaction type topic by going through the three other reaction types that we're going to learn in this course, which are gas evolution, redox, and combustion reactions. So let's get into this material here. So the third type of reaction that we are going to be learning are gas evolution reactions. And in terms of gas evolution reactions, these are probably the easiest ones for me to cover and for you to learn, because I'm not expecting you to know a whole lot about these. All that I need you to be able to do is to recognize a gas evolution reaction when you see it. In other words, if I was to write a reaction on an exam, reactants, arrow products with whatever species were there, you could recognize that that was a gas evolution reaction if it was one. So let me go ahead and kind of teach you what are the hallmarks, what are you looking for. So gas evolution reactions, these occur when two aqueous solutions, so these are just basically solutions where the solvent is water, so something is dissolved in water. Two aqueous solutions are mixed together. And one or more gases, and obviously a gas would have the little G phase label, are produced. Now, that's the definition of a gas evolution reaction. Let me go ahead and give you one other thing about this here. If you have a reaction, okay, and you have an aqueous solution where gases are being produced, the gases are going to be evidenced by bubbles. So evidenced by bubbles. And what will happen is the gases will collect underneath the, or will be present underneath the solution because that's where they're being produced. But gases are less dense than liquids, and therefore they will rise to the surface, as you always know bubbles do, rise to the surface, and they will escape into as long as that beaker's open, they'll escape into the air. So it could be just a short period of bubbling, or maybe a longer period of bubbling. But anyhow, it's evidenced by bubbles being formed. Okay, as an example of a gas evolution reaction, let me give you one. We should be able to name this compound. It does rely on you recognizing that this is one of the polyatomic ions on your list of memorized ions. And it's the bicarbonate ion, meaning that this is sodium bicarbonate, which is a famous compound. That's actually what we refer to as baking soda. If you look at your baking soda in your kitchen and you read it, it should say sodium bicarbonate. When this reacts with hydrochloric acid, which, as we talked about before, will always be aqueous in terms of its phase label. This is the type, these are the products that would form. And like I said, I would be telling you these reactions. You don't have to just figure out what's going to be formed. That's kind of a little bit beyond what we need to be able to do at this level. So it would form water, sodium chloride, which would remain dissolved in the solution, and CO2 gas. So this is an example of a gas evolution reaction, and honestly there's really only two things you're looking for. You are looking for two aqueous reactants, and you are looking for at least one gaseous product. If that is present, you have a gas evolution. A lot of times people will look for the gas product, but that's not the only thing that is required. A gas evolution reaction is when the gas evolves out of a solution. So you need the two reactants to also be aqueous. And that's all that I say about gas evolution reactions. There's not a whole lot more that we're going to need to know about these. So just be able to recognize them if you see them. And know that it would be evidenced by bubbling within the solution. Okay, so we go from the easiest type of reaction to talk about to the hardest. So that was gas evolution. And now moving on to the most difficult one. Whoops, that's not. Oxidation reduction reactions. These are really important actually in all sciences, very important in biochemistry as well. And in fact, in Chemistry 102, you would actually explore these much deeper when we do electrochemistry. But oxidation reduction reactions, first off, but you just learn them to a certain level in Gen Chem 1. First off, these are also known as redox reactions, probably just as commonly. Redox reactions, hopefully you can see the reduction, oxidation, it's just a nickname. Okay, so oxidation reactions. Oh, actually, before I go into what they are, let me be really clear about a couple things here. What do you have to be able to do? And what do you not have to be able to do? Because with each of these types of reactions, there's different expectations. For instance, with precipitation, recall, if I gave you the two reactants, you were responsible for figuring out what the two products were and figuring out which one was the precipitate and writing complete molecular, complete ionic, net ionic. With acid-base, it was kind of the same thing. You're responsible for writing. If I give you the two reactants, you have to figure out what are the products, balance it, write the three types of equations. And with acid-base, there also came a bunch of different extra pieces of knowledge. What's an acid, what's a base, monoproduct, diproduct. There was strong versus weak. There was a lot there with the acid-base reaction types. So what do you, when you're trying to organize your mind and am I meeting expectations? Am I learning what I'm supposed to? Let me be clear about what you are going to be required to be able to do for redox reactions. Okay, so number one, you are going to be required to recognize a redox reaction. In other words, if I give you a chemical reaction balanced and I give you the whole thing, you need to be able to tell me, is it or is it not a redox reaction? Some reactions are, some reactions are not. So I'm going to be teaching you the tools to figure out if it's a redox reaction. Number two, you are going to be need to be able to determine which reactant is oxidized and which is reduced. All right, that's also something I'll be teaching you today. Number three, you are going to have to be able to identify reducing and oxidizing agents. And number four, in order to do these things, what we will kind of end up doing, and what I'm going to show you how to do, is you are going to have to know how to assign oxidation numbers to atoms. Okay, so you're going to find that that's going to be a requirement for us to do all these other things. So what you do not need to do is predict products, okay? That's one thing that sometimes you need to be clear about, because, I'm not going to be giving you a reactants and saying, it's a redox reaction, figure out what the products are. It doesn't work like that with this topic. So this is all that you'll have to be able to do. So follow my examples so you can be comfortable with what's being expected. Okay, let's go ahead and define what a redox reaction is. Redox reactions are reactions in which electrons, now it can be one or it can be more, electrons are transferred from one reactant to the other. So that's really the key here, is that you have electrons being transferred from one reactant to the other reactant. If that's happening, that's a redox reaction. Okay, so let's go ahead and explore this. And the way that I teach this, because it can be a little bit confusing, I I teach it stepwise. So we're going to start with very fundamental, easy principles, and then we're going to add the layer of oxidation numbers onto it. So just stay with me in terms of my presentation. Hopefully it'll work out good for you. So let's go ahead and consider this reaction. Let's consider this reaction. We've got 2 magnesium solid plus O2 gas yields 2 magnesium oxide solid. Okay, so this is a redox reaction, and I'm going to kind of show you how to analyze these here. First off, there's 2 things that matter not at all to redox reactions. You are going to completely ignore phase labels for redox reactions. They don't matter in the least, okay? Which is kind of weird because with precipitation and acid-base, they mattered a lot. But with redox reactions, it's not about the phases because it's really dealing with electron transfers, which has nothing to do with phases. So phases, it doesn't matter. So you're going to ignore them as you're analyzing these. And actually, the other thing that you're going to ignore is the coefficients. Now, if you're doing stoichiometry, that's a different story. You always would care about the coefficients. But in terms of all the things that I've talked about that you're going to need to be able to do, analyze and identify, agents and all that stuff, coefficients are not going to matter at all. You're really just going to look at the species that are present. So the magnesium, the oxygen, and the NGO. And so what I want to have you do, at least for now, is I want you to look at the charges on, and go ahead and just write this out. I know it's a long word, individual atoms. What we want to do here is analyze what is the charge on the individual atoms here. That's what I'm saying. We're not going to care about overall, how many collective charges. That's why we're not caring about the coefficients. We want to look at what are the charges on the atoms before the reaction and after the reaction. Okay, so let's go ahead and just make a little chart here. And I want to just give you one key point. If you have an element, the charge on the element is always neutral. So all elements are neutral. Okay, so as long as you're in the elemental form, meaning there's only one type of atom present, unless you see a charge up there, which you don't, you are to always assume that it was the neutral form of the atom. So the charge on this magnesium is 0. Okay? Now, once again, this is an element because there's only one type of atom in it. It's a molecule, but remember, element versus compound deals with the types of atoms in it. Molecule versus atom deals with how many, okay? So this is definitely an element. There's only oxygen atoms in it. And therefore, by this key point here, all elements are neutral, so he has a charge of 0. When we come over to here, we have a compound. And you should know by now that this is an ionic compound, and the charge on the magnesium is a 2+ charge, and the charge on the oxygen is the 2- charge. And that's why you only needed one of each to get neutral. So now we want to ask the question, what happened? What happened to these atoms during the course of this reaction? So basically, what we're kind of just telling everybody's story. So we have magnesium atoms, and we have oxygen atoms. Let's kind of analyze what happened here. Magnesium went from being a neutral or a 0 charge to a 2+ charge. So I'm just basically breaking down each type of atom and telling his story. And oxygen went from a 0 charge to a 2- charge. Okay, so if the charges changed on the reactants, there was only one way that could have happened. Remember, the only charged particles in atoms are protons and electrons. That's it. The protons never change. They're safely inside of the atom. So magnesium could never have gained protons to get positive. That's a non-possibility. The only way that you change your charge during the course of a chemical reaction is to gain or lose electrons. That's the only currency. Remember, electrons are the currency of chemistry. They're the only thing that can come and go to change your charge. So hopefully you see that let's start with the oxygen. The oxygen got more negative, and therefore the oxygen must have gained electrons. And don't worry about how many. It's not about how many they gained so much, not at this level. We just want to know that they did. If you get more negative, you clearly picked up some extra electrons. In this case, it was obviously 2. If you get more positive, the only way to do that in chemistry is to lose some of your negative guys, okay? Which means the magnesium obviously lost electrons. All right, so if you look at the 2 reactants, he lost and he gained, which means that there was clearly a transfer of electrons, and that's all you need to know to make it a redox reaction. If he lost and he gained, that was a transfer. Just like if I give my marker to somebody else, I lose, they gain, that's a transfer. Okay, so now that we have that, we want to introduce this very helpful mnemonic device. Leo the lion goes grr. Now there's a couple of other mnemonic devices that some teachers teach. There's oil rig. I personally believe that this one is the one that just reads in the way that's the most helpful. Believe it or not, the oil rig where its oxidation is lost, it doesn't acknowledge what you're losing. I don't like that. So I think this is a better mnemonic device. Now, when you see Leo, don't just think 3 words. Think an entire sentence, okay? Let me give you the words that you want to use. Trust me on this. The one that lost electrons, which can be 1 or more, was oxidized. Notice I'm using, I think in English, it is the passive tense. The one that lost electrons was oxidized. Don't just think lost electrons oxidation. Don't do that because you're going to get messed up when you come to the agents. Remember, or just train yourself to say this exact same sentence every time. And the one that gained electrons, that's the G, electrons, 1 or more, was reduced. That's the GER. So once again, passive tense. So what I usually do is this. When I look at the charges, I actually usually go for the GER first. I see whatever one got more negative, and I just say the one that gained electrons, because he clearly gained electrons if he got more negative, was reduced. And I just write GER reduced. And the one that lost electrons was oxidized. Obviously, you get to a point where you can do this in your head, but until you're trained at it a little bit more, just write it down. So hopefully you're with me. I think it's easier to see the reduced one. The one that got more negative picked up electrons, gained electrons, and he was the one that was reduced. Okay, so that's how you're going to be able to tell which reactant was oxidized and which was reduced. Tell their stories, see which one got more negative. He's the one that got reduced. So oxygen got reduced. Now, we also need to deal with what's this thing called a reducing agent and an oxidizing agent. And this is a little vice versa thing here. Whatever one was reduced, which in this case is the oxygen, he gets labeled the oxidizing agent. I'm just going to write OA, the oxidizing agent. Whatever one was reduced is the oxidizing agent. Whatever one was oxidized is the reducing agent. Now, what's that all about? Clearly you can see we do a vice versa. You do a switch. The reduced one is the oxidizing agent. The idea here is the agent is like the doer, the cause. Okay, so think about this here. If I give somebody this marker, I have lost a marker, they have gained it. But I was the cause of their gain. Does that make sense? It was me who caused that in the other person. It's kind of the same thing here. When you think about this here, let's say the magnesium. because he was oxidized, meaning he lost electrons, he was the cause of his gain. And that's why we call him the reducing agent. He was the guy that caused somebody else to gain something. And same thing with the oxygen. Because he was reduced, because he gained electrons, he was the cause of somebody else's oxidation. Somebody else's loss was his gain. Kind of your loss is my gain type of thing. So that's how you're going to identify reducing and oxidizing agents. It's very simple. Just do a switch. Okay, now let's go ahead and do another one where we can have a little bit more, we can talk about another aspect of this that can get confusing. Let me have us do, let's see here. Yeah, this one here. Let's consider this reaction. 2 Al3 plus, I'm even going to leave phase labels out of this guy, plus 3 calcium goes to 3 Ca2 plus 2 aluminums. So if I was to ask you, is this a redox reaction? And if so, which species is oxidized and which one is reduced? And by the way, you're always focusing on the reactants. One of them gets oxidized and one of them gets reduced. Because remember that in the definition, it was a reactant transfers electrons one to the other. And then the other thing is which one is the reducing and which one is the oxidizing agent. So for now, go ahead and write charges. I'll leave out the words on individual atoms, but we're basically going to kind of see what happened to everybody's charge. Once again, you are completely ignoring the coefficients. So his charge is obviously 3 plus. His charge is 0. If nothing's listed and it's an element, it's always 0. His charge is 2 plus, and his charge is 0. So when we go to see what happened, which is really what you want to do. Now, you don't have to write the words what happened, but for now, maybe in your notes you should. What happened to aluminum and what happened to calcium? Aluminum went from being 3 plus to 0, and calcium went from being 0 to 2 plus. Now, first thing I want to say is this. Don't worry that it seems to be like one of them had a 3 electron difference and one of them had a 2 electron difference. We are not concerned at this point with those numbers matching, but what you should see is that one of them gained electrons and one of them lost electrons. So can you tell which one, I always think gaining is easiest to see first. Can you tell which one gained electrons? Which one gained electrons? It's a little bit harder than the previous one. The reason it's a little harder is because in the previous one, if you notice, one of them went from 0 to 2 minus. So it's very easy to see that it got more negative because it entered the negatives on a number line. Whereas here you have no negative numbers. But that doesn't mean that one of them didn't get more negative. If you get tripped up, and as a student, I feel like I used to get tripped up on this, draw yourself a old-fashioned number line. It really does help some people. Draw yourself an old-fashioned number line where positive numbers are up here, negative numbers are down there, and zeros in the middle. And then just see what's going on. So aluminum, if aluminum went from 3 plus, let's just say it was right there, towards 0, hopefully you see he got more negative. Okay, that's very helpful. And the one that got more negative clearly gained electrons. That's the only way to get more negative. So the one that gained electrons was reduced. So the aluminum was clearly reduced. Calcium went from 0 to positive 2. And he got more positive. If you get more positive, the only way you can get more positive is to lose some of your negativity, lose some of your electrons. And so this one is the one that lost electrons and was oxidized. Okay, so therefore we have the first part, identifying which species was oxidized and which was reduced. So he was reduced and he was oxidized. Now the agents, which one is the reducing agent, which one is the oxidizing agent? Just do a vice versa. The calcium is the reducing agent. So you could label it right here if you want. The calcium reactant is the reducing agent because you just vice versa what happens. So the oxidized one is the reducing agent, and the reduced one is the oxidizing agent. So this is the oxidizing agent. Once again, we're only trying to label the reactants. The products don't really get a label in this context. Okay, so that's the other thing I want you to notice is that a number line can be helpful for figuring out which one got more negative, which one is reduced. And then, of course, the other one is going to always be oxidized. Anytime there's a transfer, just logically speaking, if one person loses, the other person has to gain. So transfers, you'll always have both. You're never going to have both species get reduced. That's an impossibility. All right, so that is what a redox reaction is, and it seems like we're almost done, and it seems like it should be, maybe it isn't that hard, but I told you it was hard. So there is like a little missing thing here which we have to venture into. And what we want to talk about is, let's label this next part oxidation numbers, otherwise known as oxidation states. Oxidation states is the old-fashioned term, but it's used quite a lot still. Oxidation numbers seems to be replacing it, but it means the same thing. So let's go and entitle this next part of your notes oxidation numbers. And what we're going to be talking about is on Blackboard, you will have a set of rules. It's straight from your textbook as well, although I did kind of rewrite it and rearrange it a little bit. But it looks like this: rules for assigning oxidation numbers or states in order of priority. And it also has this table, attached. Okay, so we're going to get to this, how to use the rules. And the good thing is it is about just obeying rules, which most people are pretty comfortable with. However, we want to spend a little bit of time before I jump into that rules, because honestly, what I could do if I was just lazy is just tell you how to do these rules. And that'd be fine, and you'd get the right answers for the most part on the test. But what you wouldn't do is you would have no sense of what you were doing or why you were doing it. And if you advance in chemistry, you'd be behind. You really want to understand what in the world is an oxidation state, not just how to assign them. So I don't want to leave you missing something important, because these are actually pretty important in organic chemistry. Okay, so to explain this, let's consider this reaction. Let's consider this reaction here. So 2H2 plus O2 yields 2H2O. And let's actually ask the question, is it a redox reaction? By the way, in the previous two examples, I just told you they were redox reactions. But how did you know they were redox reactions? Like, I mean, I told you at the front that they were. The key here is that if there is a transfer of electrons, that's what makes it a redox reaction. Okay, that's really the hallmark of a redox reaction. So if you remember that whole what happened thing, if you see the charges change, it's a redox reaction. If they don't change, it's not a redox reaction. And frankly, there's a bunch of reactions that are not redox reactions that you could analyze the same way, and you'd say the charges never changed, and then you would see it wasn't a redox reaction. All right, let's go to this one. Let's ask, do the charges change? Is it a redox reaction? So let's go ahead and start out the same way. We're going to look at the charges on individual atoms. And we see that this one is hydrogen. It's an element, so he's 0, and then oxygen is a 0. When we come over here, we hit the problem, which is H2O is not a compound that contains ions. Remember with the MgO, that was an ionic compound. So Mg was 2+, oxygen was 2-. H2O is a molecular compound. As you know, it has covalent bonds. There are no ions, and therefore there are no charges. Now I know I talked about partial charges and all that, but we're talking about what is a full, is it 1+, is it 2+, is it 1-, is it 2-, and there are no ions in this molecule because it's not an ionic compound. However, what we're about to find out is that you can still have a transfer of electrons, but it's just a partial transfer. It's not a full give it away complete transfer. It's a partial transfer of your electrons. So let me go ahead and see if I can explain this here. Let's go ahead and just write this in your notes, and let me assure you, you do not need to know, you do not need to do what I'm about to do for me on the exam. You don't have to do all of this analysis every time you have a redox reaction, because like I said, in the end of the day, you're going to be assigning stuff, and it's going to be much easier. But I want to at least try to kind of bring you along on understanding what in the world these things are. Let's go ahead and talk about the point of view of the hydrogen atom. I think that's the best way to do this. Let's kind of think about what's happening with the hydrogen, the hydrogen atoms, I suppose you could say. So we have H2, which, as you know, is the one hydrogen atom bonded to another hydrogen atom. Maybe you didn't know that, but they're both nonmetals, which means they're held together by covalent bonds. And I suppose maybe you didn't know that, but it is just a single bond, so H to H. So you didn't have to know that, but now that you do know. So a covalent bond is a set of two electrons, which is shared between the two atoms, okay? So sometimes you could write it like that. Okay, so each of these electrons, they're shared equally between this hydrogen and this hydrogen, because the two hydrogens are both pulling on them equally. So in a way, you could say that he has one and he has one, kind of, if you kind of divvy them up equally. And that's actually why you think of it as neutral, because it really is, the hydrogen has a proton and an electron, which gives it a zero charge. Same with this one. But really, the idea is that you have equal sharing of those two electrons. But let's see what happens when you incorporate those hydrogen atoms into the water molecule. We have talked about this a little bit in previous discussions. So actually, we can kind of reuse a little bit of that. As you know, this H2O molecule has two covalent bonds. So I just rewrote that dash as the two electrons that they are. As we talked about before, when you're looking, let's just look at this bond right here. Those two electrons are not shared equally. One of the atoms pulls much harder on them than the other. And if you remember, it's really oxygen that pulls harder. So really, it's more like this. The electrons are pulled much tighter by oxygen. So they're really more like that. So the idea here is this, is that hydrogen used to comfortably have an electron to himself. And now it's kind of been transferred to oxygen. That's what I'm talking about. It's a partial transfer. Can you kind of see there's been a little bit of a partial transfer of an electron? And believe it or not, that's enough to interest chemists. You're tracking where the electrons are, and they used to be kind of, shared by, or, given to this hydrogen or whatever, and now it's quite far away. So it is kind of like he's losing it. He's not losing it completely, because it's not like it's an ion, but it's still a covalent bond. There is some sharing, but it's not as equal as it was over here. And that partial transfer is enough to qualify as a redox reaction. Now, let's go ahead and explain what oxidation numbers are. Oxidation numbers. Oxidation numbers are like an imaginary thing, but basically what they are is this. Oxidation numbers are the charge, and I'm putting it in quotes because it's not actually an electric charge like +1, +2. But it's the charge an atom would have if. Notice the hypotheticalness of this. If the bonded electrons were given, or actually let me use the word assigned, were assigned to whatever atom pulls them tighter. And that is what an oxidation number is. So in red, let me go ahead and explain to you the oxidation numbers here. And once again, I'm only focusing on hydrogen to make my point. Since these both pull equally, you can't say that one pulls them tighter. So you just kind of split them in half, and the hydrogen atom would have a 0 charge, because remember, 1 proton and 1 electron gets you 0. And frankly, this hydrogen would also have a 0 oxidation number. So this is the oxidation number. I'm just going to label from the point of view of one of the hydrogens. Come over here. What we're doing is we're basically assigning the electrons, these guys, both of them, to the atom that pulls them tighter. So we're saying, guess what? Oxygen, keep it. You get to keep them. Let's think about what the hydrogen's charge would be if, and that's the idea. What would hydrogen's charge be if we just said, take the electrons, oxygen, and you still have the proton in there. Don't ever forget, hydrogen has a proton in its nucleus, but no electrons. And that gives you a +1 oxidation number. Now, you're going to see something that I just did. When you have charges, classic charges like the magnesium 2+, charges always have number then sign. That's what you do for like a charged particle, like an ion. When you have oxidation numbers, you do sign then number. It's just a way to differentiate a real charge, like on an ion, as in opposition to an oxidation number, which is just a hypothetical charge. Because it's not really that the oxygen fully takes this electron, it's just that we just give it to him. It's a way for scientists to track where the electrons are moving, even if they don't move all the way to the other atom. So that's what the oxidation numbers are. In H2, it's a 0. In water, the hydrogen has a +1. So that's good enough. And I always tell students, if you got 30% of that, you have what you need. You don't have to have 100% of that at this point, because I recognize that there's things that we're skipping over that wrap around later in the semester that will give it full meaning. So don't stress about if you didn't get it all. Now, from here on out though, now that I have discussed oxidation numbers, or at least introduced them, I want us to make a change into how we approach redox reactions. Leave the reaction here, or maybe just recopy it in your notes. When I introduced redox reactions, I used the word charges right here. And I did that because it's easier to teach redox reactions with ionic compounds or with like ions. And you'll notice in the 2 examples that I gave you, they were involved like true ions. But redox reactions can expand to things that aren't ionic compounds. And because of that, no matter what from here on out, no matter what kind of reaction you're looking at, instead of writing charges, I want you to always write oxidation numbers on individual atoms. Now, you don't have to write the on individual atoms. It's just a recommendation so that you don't get tripped up. And I'll explain that in just a minute. But this will allow you to analyze any reaction, not just ionic compound ones. And so let us talk about how are you supposed to know what the oxidation numbers are on this. You do not need to be drawing bonds and all that. That is not the goal for you to start analyzing stuff that's beyond where we are. That was just an explanation. To assign oxidation numbers, you use rules. So if you haven't already printed out, print out the rules for assigning oxidation numbers, which is under course documents, extra study sheets. You should just always have this with you on exams or quizzes. And really, it's just about knowing how to analyze it. Okay, so let's go ahead and we'll do these ones first, and then we'll do some more practice. So first thing I want you to notice is it says rules for assigning oxidation numbers, or states in order of priority, which means that the top rules are more important, so to speak, or at least they have to make sure you're satisfying them before you get to move down. So the way that I wrote this, and I typed it up, and I think it's a little bit better than what the book had, is you have 2 groups here. Oh, can you add the word, so it says elements, add the word and write monoatomic ions. monoatomic ions, because polyatomic ions get dealt with later down here. So this should say elements and monoatomic ions, which would help us over here because these two are both elements. So free elements, and free just means, I mean, you could almost cross out free. It just means not involved in a compound. So it's a little bit redundant. Elements always have an oxidation number of 0. I'm looking at rule number 1 here. So if you are an element, you're always going to write a 0. And you'll notice it is the same as the charge, what I talked about before. There's a lot of similarities between oxidation numbers and charges. So that's why it wasn't really bad for me to go with charge first. It's just that this is a broader umbrella to basically contain, deal with any chemical species. Okay, so elements are always 0, end of story. If you have a monoatomic ion, then the oxidation number would equal their charge. We'll do some practice with that one in just a few minutes, but we don't have any monoatomic ions here. Monoatomic ions would be something like that. That would be a monoatomic ion. 1 atom ions. Okay, so over here, the water is a compound because you have both hydrogen and oxygen atoms in it. So that would have you jump over to your compounds. And what you have to do is you have to take your eyes and always look at rule 3 first, because this whole concept of priorities. You have to think about rule 3 and make sure it gets satisfied. Rule 3, the A says the sum of the oxidation numbers of all the atoms, maybe underline the word all the atoms. That's an important concept. In a neutral compound is 0. So rule 3A deals with neutral compounds, meaning that you see nothing up here. And as long as you don't see anything, it's a neutral compound. And by the way, compounds are neutral, okay? Look at rule 3B. 3B says the sum of the oxidation numbers of all the atoms in a polyatomic ion. So the opposite of a neutral compound would be something like a polyatomic ion, where it's, it has both phosphorus and oxygen, but you actually have a charge. So polyatomic ions versus neutral compounds. Okay. So what these rules tell you is that you are going to have to make sure that the oxidation numbers add up to 0 if the compound is neutral, or the charge if it's a polyatomic ion. Okay, so that's what rule 3A is. But the way this works is you kind of have to just store that in the back of your mind. You're going to make sure that you satisfy that rule soon, but you have to store it in the back of your mind. And then just proceed a little longer. So rule 4 deals with group 1 and group 2 metals. Group 1 and group 2 metals are just the first 2 columns of your periodic table, your sodium, your calcium, and all that. We don't have any group 1 or group 2 metals. Hydrogen is group 1, but it's not a metal. Okay, so we can pass over that rule. That rule does not help us with this H2O. Rule number 5, in their compounds, nonmetals. Okay, that's good because we've got 2 nonmetals here. Nonmetals have oxidation numbers according to the provided table, but nonmetals higher on the table always take priority. So then you move on to this table. This is the table that deals with rule 5. See how I wrote rule 5 right there? So what you do is you want to scan your eyes from top to bottom, and whatever element you see first, that's the one you write down first. So I see hydrogen first, and hydrogen has a +1. Now, do you remember when I explained it, hydrogen had a +1? It did. I wrote it in red. The rule will get you to the same thing that the explanation will, but you don't need to do the explanation from here on out. Just use the rules. Now, once you assign hydrogen, and you only have 1 guy left, which is, oh, by the way, this is important. The reason I've been writing on individual atoms is this. Yes, there are 2 hydrogens, but the number that you record right here is the number on the individual hydrogen. You always just record it as +1. Hydrogen is always +1. Yes, there are 2 hydrogens. We know that. They both have a +1. But you don't write +2. That's an important thing. And you certainly don't do anything with the coefficient. Okay, you just record what is the oxidation number on that individual hydrogen, +1. But when you only have 1 type of atom left, oxygen, it's not about this chart anymore because you have to revert back to rule number 3, which was the most important rule. Remember, order of priority. And it says the sum of the oxidation numbers of all the atoms in a neutral compound has to equal 0. If it's a neutral compound, they have to add up to 0. So this is how this works. Ignore the coefficient completely. There are 2 hydrogens. They each have a +1. If you want to, you could record both of them, as long as you erase that later. But there are 2 hydrogens and they both have a +1. What will oxygen have to be so that they all add up to 0, and it would be a -2? That's what his oxidation number must be so that all the atoms add up, oxidation numbers add up to 0. If you know how to draw the compound, certainly you could do it like this. -2 for him, +1 for him, +1 for him. But we haven't really learned how to draw most molecules yet, so that wouldn't really help you with most of the things. But at the end of the day, you don't really want to record that second one. You should just have one number recorded for each type of atom. And from there, you can do the analysis. What happened to hydrogen? What happened to oxygen? Hydrogen went from 0 to +1. Oxygen went from 0 to -2. See, everything is the same from here on out. Which one gained electrons and was reduced? I can see it right away. Oxygen gained electrons and was reduced. Hydrogen lost electrons and was oxidized, making oxygen the oxidizing agent, making hydrogen the reducing agent. So all the rest of the analysis is quick. It's all about, can you assign oxidation numbers? So actually, what we're going to do now is some practice at assigning oxidation numbers, and then we'll take this to some more chemical reactions and do a little bit more analysis. All right. So practice for assigning oxidation numbers. Assign oxidation numbers on each individual atom. See, every single atom gets an oxidation number. Okay, it's not an overall charge. Every atom, every letter gets an oxidation number. So let me give you a bunch of different ones to practice. Let's just put this on in our notes. And this is all about following the rules. I'm going to give you 9. Bunch of different things here. All right, so you get that down, and let's just, if you want to pause the video and give it a try, you'll be using these rules, addressing them in order of priority, and which we'll sometimes use, if you're in rule 5, it will use this table as well. But I'm going to walk us through assigning oxidation numbers. But try it yourself first. All right, chromium. Chromium is an element. There's no charge on it. It's not an ion. It's just a free element, and those are always 0. Done. Chromium 3+ is a monoatomic ion, and it will have an oxidation number equal to its charge. So if its charge is 3+, you would write +3. And by the way, this is not a major live or die type of distinction, but we might as well do it the same. The book does it the same, and convention is to switch the order of the number and the sign. But that would be the oxidation number on chromium 3+. CCl4, which is carbon tetrachloride, is clearly a compound, right? It's either going to be a neutral compound or it's a polyatomic ion. And if you don't see anything up here, that is a neutral compound, which means that all the atoms, that's the terminology, all the atoms, when you add them up, that's what this word sum means, are going to have to add up to 0. All the oxidation numbers will have to add up to 0. But we need to start with something first to know like how to get them to all add up to 0. So you just proceed down a little longer Find out if you have any group 1 or group 2 metals, and you don't. So in their compounds, nonmetals, which both carbon and chlorine are, will have oxidation numbers according to the table, and you do this table in order of priority. So you scan down until you find either carbon or chlorine. And chlorine is a group 7A, and it therefore is a -1 oxidation number. That's the number you write down. Now in your mind, you recognize there are 4 chlorines. They will all, every atom gets an oxidation number, every atom. They will all come in with a -1 oxidation number. So if you are trying to get all the oxidation numbers to add up to 0, carbon would have to provide a +4 oxidation number, and he does. So that's what you would write down if you're trying to get oxidation numbers. Notice, I don't write -4. That would be the wrong thing to write because you're writing them. Think of oxidation numbers as individuals, like social security numbers. Everybody gets their own, okay? So you don't get like a net overall, but you do consider that there are 4 of them when you're trying to figure out the sum, okay? SRBr2. Once again, a neutral compound. No charge, neutral compound. They're going to have to all add up to 0. With this one, though, I believe you're going to find a group 1 or group 2 metal. So go to your periodic table and find strontium. Strontium's a group 2 metal. They will have oxidation numbers of +2. And once there's only one type of atom left, this rule's got to kick in. You got to make sure you give it the right number so that they all add up to 0. There are 2 bromines, so hopefully you see that if they have oxidation numbers of -1, there are 2 of them. When you add that to +2, you'll get 0. I want you to notice with this one here, 4 ionic compounds, like our good old-fashioned ionic compounds where you've got the metal and the nonmetal, metal cation, nonmetal anion. The oxidation numbers are just the same as the charges. For ionic compounds, which these ones were not, but this is an ionic compound. Do you notice it is strontium 2+. It is bromine minus. You know, bromine's a halogen. They form 1-. It's not any different for ionic compounds. But it's really molecular compounds where oxidation numbers are really, really helpful. Here, we have a neutral compound. There's no charge up there. If it was trying to be the sulfite anion, I would have written SO3 2-. It is not written, therefore you don't imagine it to be there. That is sulfur trioxide. That's a molecular compound, neutral. So we're down here. They're going to have to all add up to 0. Take your eyes a little lower. See if you have group 1 or group 2 metals. You do not. And now rule 5 kicks in for your nonmetals. Now, who gets priority? One of them is going to get to be assigned first, sulfur or oxygen. Who do you see first? Oxygen. Oxygen gets -2. Now, only one guy left. You've got to make sure they all add up to 0. That was the most important rule. By the way, if you don't get this concept, you might say, oh, and sulfur is group 6. That would also be -2. But you would be writing the wrong oxidation number because what you're doing there, if you give sulfur the -2 that it says, you are not acknowledging that this was the most important rule. They've got to add up to 0. And if you had put a -2 right there, they would have not added up to 0. So the oxidation number of sulfur is actually +6. Because there are 3 oxygens, each of them gets you a -2. -2, -2, -2 gets you -6. This would have to be +6 so that when you add all of them up, you get 0. Remember to add them, it's the same thing with charges in a sense. Equal numbers of positive and negative charges gets you 0. Okay, that's kind of another way to think of it. This here is your friendly nitrate anion. That is a polyatomic ion. Now, we haven't done this one yet. The sum of the oxidation numbers of these has to equal the charge on the ion. So in your mind, you're going to have to make sure that when you add these all up, they equal -1, not 0, -1. It was 0 for neutral, which makes sense. There's a 0 right there. But adding up to the charge. So we're going to skip rule 4 because that's group 1 and group 2 metals. Rule 5 deals with nonmetals, which both of these are nonmetals. Who gets priority, nitrogen or oxygen? Oxygen. Oxygen is first. So oxygen is -2. There are 3 of them there, so the oxygens all together will give you -6. So what number would nitrogen have to come in with? There's only one nitrogen. What number would nitrogen have to come in with so that you add up to -1? And the answer is +5. Nitrogen's oxidation number is +5 in nitrate. Come over here to KNO2, potassium nitrate. Now, with this one here, there's actually 2 ways to do it. What you could do is you could recognize that potassium nitrate is really the K+ ion and the nitrite anion. And you could assign the oxidation numbers at this level. Let me do it like that on top. So that's a monoatomic ion, and his would just be +1, the K+. And NO2, it's very similar to this one, NO3. We just found out that oxygen is a -2 oxidation number. And these will have to all add up to -1, so that gets you -4. So what would this nitrogen have to be so that they all add up to -1? And it's going to be +3. So that, frankly, is kind of how I would have done that one. And you'll notice that when you think of it as the neutral compound, which it is, see, once they're together, you can think of it as being a neutral compound. You'll see that they do add up to 0. You've got 2 oxygens, -4, and then +4. The second way to do this, and it will lead you to the same answers. So if you're good with that, just do it that way. The second way to do this is to, from the start, just consider this a neutral compound, which it is. When it's all together, it is neutral. And then just follow the rules. So they're going to have to add up to 0. Group 1 metals always have a +1, so you just assign that one. And then just keep progressing. In their compounds, non-metals have oxidation numbers equal to their charge, and see who you see first. So it's almost like assigning the first priority is him, second priority is him, and then this one will come in and be whatever it needs to be to add up to 0. And you will get the same thing, +3. +3. I just realized something. I want to change this one to a different one. One of the most tricky molecules to assign is hydrogen peroxide. So let's do him. But if you just follow the rules, you'll get the right answer. Hydrogen peroxide is a neutral compound. So we're going to start with this rule. They're going to have to all add up to 0. You don't have any group 1 or group 2 metals, so we're going to go straight to the non-metals. Who gets priority? Hydrogen. See how hydrogen is above oxygen. Hydrogen gets a +1. And now, what would oxygen have to be so that when you add up all the oxidation numbers, they add up to 0? So there's 2 hydrogens, that will give you +2. And there's 2 oxygens. Well, oxygen is going to have to be -1. -1. That's going to be the only way, because you're going to get +2 and -2. Now, this is one of the very few times where oxygen is not a -2. Oxygen is almost always -2. This is one time where it's not. One of the other times, be very careful, is the element oxygen. That would always be 0. Okay, but I just wanted to do that one. And then let's just finish out with this one. Polyatomic ion, so they have to all add up to -1. These are both non-metals, so you're going to use this chart, and oxygen gets priority over chlorine. This is the chlorate anion. What would chlorine have to provide in terms of oxidation numbers so that when you add them all up together, all the atoms, 3 oxygen atoms that each have a -2, chlorine is going to have to give you a +5. Because +5 and a -6 gets you -1. So that's assigning oxidation numbers. Now, you want to get good at that. There's plenty of practice in the book. Now let's bring this all together and analyze a more complex redox reaction than ones that we've been doing so far. So, how about this guy here? And let me ask it in the form of a question. Is this a redox reaction? That's going to be a yes or no answer. And it's yes if the oxidation numbers change. It's no if the oxidation numbers do not change. And let me do an if so. Let me have you just identify let's have you guys identify the reducing agent. Understand with these redox reactions, there's a bunch of different ways you can ask the question. You could say identify the oxidizing agent. You could say identify which reactant is reduced, which reactant is oxidized. No matter what the question though, I just analyze it from start to finish and keep it organized in my brain, and then I just answer the question. I think that's a very healthy way to do it. Just kind of use a methodology. So let me write the reaction down. Tin, solid tin, plus 4 nitric acid. Now I'm writing the phase labels just because I have them, but as you'll remember, they do not affect redox reactions, nor do the coefficients. SnO2, solid. By the way, what's his name? Let's think about that for a minute. Tin 4 oxide, because this tin has a 4+ charge. Plus 4 NO2, so that's nitrogen dioxide gas, plus 2 H2O gas. Okay. So is it a redox reaction? We have to assign oxidation numbers on every atom. Every atom gets an oxidation number. Tin, that's an element, 0. Let's come over here to HNO3. Okay, ignore the 4. That's a neutral compound. So they're going to have to all add up to 0. At a certain point, you can almost memorize these. It's actually not as hard as it seems. Rule 4 deals with metals. We don't have metals here. Rule 5 deals with the non-metals. Let's give them an order of priority. Who gets first priority? Who's highest on this list? Hydrogen. +1 for hydrogen. Who is second priority? Oxygen. And once you only have one guy left, that's when you always have to revert back to make sure they all add up to 0, because that's your only time that you get to make sure they all add up to 0. What does nitrogen have to be in order to make sure they all add up to 0? Well, I'm seeing +5. +5 for the nitrogen, because then you've got 6 pluses and 6 negatives. Okay, over here, tin and oxygen, you have a neutral compound. They're going to have to all add up to 0. I don't have a group 1 or group 2 metal in tin, so that's okay. Now I'll just go to this one here. Oxygen is who I see first. So oxygen is -2. Tin is going to have to be a +4. And by the way, yes, once again, for ionic compounds, it is what the charges were. Okay, that's going to be fine. This is the deal. What some students might, if they're not getting what's going on here, they might look at this, and if you're being too robotic, you might be like, oh yeah, nitrogen. Nitrogen's in this column. Nitrogen is always -3. No, wrong. That's when nitrogen is the anion in an ionic compound with a metal. That is not at all the context here, and you can see it's not a -3, it's -5. So you have to kind of do things correctly in chemistry. You can't just kind of do your own thing. All right, NO2. I'm just going to start going through this a little bit faster. Oxygen is the priority, and this nitrogen would have to give you a +4 to get them to add up to 0. H2O, by the way, H2O we've already done, and it will never be different than hydrogen is +1 and oxygen is -2. So now the question is, what happened to all the atoms? And I just make a list. We have tin atoms, we have hydrogen atoms, we have nitrogen atoms, we have oxygen atoms. So let's tell everybody's story. Tin went from 0 to +4. Hydrogen went from +1 to +1. Nitrogen went from +5 to +4. And oxygen went from -2 to -2 in all contexts. So, is it a redox reaction? Well, there are a few atoms where the oxidation numbers didn't change, but as long as the oxidation numbers changed on really 2 of them, 1 of them got more negative, 1 got more positive, it's a redox reaction. So this is a yes. So without even trying to answer this question, let's just analyze it. Leo the lion goes grr. Who gained electrons and got reduced? This one. The nitrogen clearly got more negative. On a number line, he headed that way. +5 to +4 is headed towards the negatives, which means the nitrogen is the oxidizing agent. You do the vice versa. Tin lost electrons and was oxidized, meaning that he is the reducing agent. So now I'll look at what the question was, because I don't want to get too distracted. The question was to identify the reducing agent, and therefore I would say tin. Now, if the question had said identify the oxidizing agent, in some contexts, they would just want you to say nitrogen atom. In other contexts, they would say, you know, whatever reactant contains that atom. Really, either is fine, and I don't want you to get tripped up on that. Mine would come in the multiple choice, and I would never give you both that you had to choose from. It's either going to be for the oxidizing agent, either you would say nitrogen, or you would say the molecule that contained him. You could call this the oxidizing agent. I've seen it done both ways. All right, that is redox reactions. So we'll have more practice with that in other ways in the book and whatnot. I am going to call that it for the redox reactions and move into combustion reactions. Combustion reactions are the last type of chemical reaction, and we will also be doing combustion analysis, and then the video is over. So let's go ahead and just finish this up with combustion reactions. Actually, I'll just label this the singular, combustion reaction. A combustion reaction is a type of redox reaction, believe it or not. That's why I teach this one last, because I like to kind of accentuate that it's a type of redox reaction in which an organic compound, and to be organic, you really just have to contain carbon and hydrogen. It contains carbon and hydrogen. Now, let me stop on that just for a second here. Some organic compounds like C3H8, C4H10, or frankly CH4, are called hydrocarbons. Hydrocarbons just contain carbon and hydrogen. You see that? So this term hydrocarbons is something we're going to end up using in a little bit. Just carbon and hydrogen. Now, it's not up to you to just know like a bunch of memorized things. But if I give the formula to you, you should recognize that that is a hydrocarbon. Whereas something like C6H12O6 or CH3OH, that is glucose, sugar, glucose. That is methanol, which is a type of alcohol. These are both organic compounds too, because they contain carbon and hydrogen, but they're not hydrocarbons, okay? So combustion reactions can use either of these types, but I just wanted to mention what a hydrocarbon was. So a type of reaction in which an organic compound is burned, so combustion is burning in the presence of oxygen. That's why when you try to get rid of a fire, you smother it. You're trying to get rid of the reactant oxygen. Producing two compounds, CO2 and H2O, and a whole lot of heat energy. Okay, so you're going to have a lot of heat come out, which is why they make fireplaces. Fireplaces are combustion reactions, and the heat comes out and you warm yourself up. That's why the engine of a car gets hot. That's combustion reaction. You're burning octane. It's producing those two molecules, and the engine of the car gets hot. So this is the basic format of a combustion reaction. Sometimes you can get other products, but for this class, 2 products, CO2 and H2O, because our organic compounds are going to be fairly simple. So let's first off prove that these are redox reactions. Let's start with that first. So let's burn methane. I think I've introduced this before, but this is the molecule methane. This is the component in natural gas that you're burning. If I asked you to write the combustion reaction for methane, you should be able to do it, because I actually kind of told you what all the pieces are. Whatever the organic compound is, you're going to react it with oxygen, and you're going to produce the same 2 molecules every single time, CO2 and H2O. And then you just have to balance it. So go ahead and balance this. I think we've done this one before, possibly, but the balancing should be pretty easy. Can you prove that it is a redox reaction? Let's do that together. And if so, let's figure out what is the oxidizing agent. Let's ask what is the oxidizing agent. So is it a redox reaction? We are assigning oxidation numbers. And I'm going to go through this a little bit fast. If you want to pause the video and use your rules, it will get you the same things that I'm about to put on the board. All right, so I've got oxidation numbers on every type of atom, every letter. Every type of letter gets an oxidation number. And let's find out what happened to everybody. Carbon went from -4 to +4. That's really all you need to see. It's definitely a redox reaction. If the oxidation numbers changed, it's a redox reaction. Let's figure the rest out. Hydrogen went from +1 to +1. Oxygen from 0 to -2. All right, which one gained electrons and was reduced? That must have been the oxygen. He got more negative, meaning that he is the oxidizing agent. And that is the answer. Oxygen is the oxidizing agent, which is where the term oxidizing agent comes from, because oxygen is a fabulous oxidizing agent. If you want to just finish this out, clearly the carbon was oxidized. He got very much more positive, and that makes him the reducing agent. So you could either say carbon or you could say the methane. Okay, so it's clearly, and if you did this analysis on any redox reaction, any combustion reaction, then you would see the same thing. They're all redox reactions. The second thing that I'd like you to be able to do is to write redox or write combustion reactions if I give you the thing, the compound, the organic compound that I'm trying to ask you to burn. So let's give an example here. Can you write the combustion reaction for, let's go ahead and have you burn methanol. That'd be the only thing that I tell you, methanol. Well, you just write what you're trying to burn. The second reactant will always be oxygen. And the 2 products will always be CO2 and H2O, the most famous 2 small molecules on the planet. Okay, so pretty easy to remember. And then you just balance it. So, tip. When you balance combustion reactions, there's an order that I recommend doing it. You always balance the carbon first, then the hydrogen. Oxygen gets balanced last. That's the way that you should balance combustion reactions. So think about carbon first, then hydrogen, then oxygen. It will make it easier on you. So carbon is looking good because I've got 1 carbon here and 1 carbon here. Hydrogen. I've got 4 hydrogens. Be careful. Sometimes the hydrogens get separated. 4 hydrogens here, and I can get 4 by putting a 2 right here. And then, let's see here, oxygen last. 2 plus 2 more is 4 oxygens on this side. Oh, this is a good example here. We got him there. So if I put a 2 right here, I actually have 5 oxygens, and that's a problem. This is what I would consider almost like, oh shoot, I'm in a brick wall. With combustion reactions, when you can't easily see how to finish this out and just, if there's no number you can put here, don't be tempted to put like a 3/2 or whatever here. That would be unwise. I wouldn't recommend that technique. What I would say is this is how I would think of it. You just tried to balance it when there was 1 methanol and it did not work. It didn't work easily. So clearly this is not a 1. With combustion reactions, I think this is a good technique. It didn't work easily when that was a 1. So try it with a 2 and see if it falls into place. 2 carbons, 2 carbons. 8 hydrogens now, because that's 4 times 2 is 8. I'll get that here. And now oxygens, I've got 4 plus 4 more is 8. I've got 2 here, and so I need 6 here. And that is the balanced combustion reaction for methanol. So these actually, let me give you one to practice at home. Could you balance the combustion reaction for C3H8? Let's have you do this one at home. Write the reaction, put the species down, O2, CO2, H2O, and then balance it. You can always just Google the answers. These are all over the internet to make sure that you're doing it right. But I would like you to know how to write and balance a combustion reaction. The last thing that we need to do, and then we're done with this video, is combustion analysis. This is a topic from an earlier chapter. I believe it was in chapter 3, which I skipped at the time because I like to do combustion analysis later when we actually have talked about combustion. So let me go ahead and grab my papers where I've got my numbers. Combustion analysis. Let's go ahead and write what it is. It's really it's a lab technique. It's a lab technique, kind of famous, that is used to determine the empirical formula of an organic compound. And I will assure you that we will only be doing hydrocarbons. The hydrocarbon combustion analysis is much easier than if it contains something else besides C and H. So we're going to leave it at the kind of bottom level here. We will only be doing combustion analysis of hydrocarbons where you only have C and H. We have a new term here, empirical formulas. So I saved this as well for this topic. This was also something, it was either in chapter 2 or chapter 3. Empirical formulas versus molecular formulas. All right, so let's start with molecular formulas. Molecular formulas tell you the actual number of atoms in the compound. And this is basically the normal type of formula. We have been doing these or using these the whole time. So molecular formulas are things like, let me use this one, C6H12O6. Let me do hydrogen peroxide. I think I mentioned that one earlier. That's hydrogen peroxide. Let me do, this thing is called propane, but you don't have to memorize that. So molecular formulas, basically, the subscripts are telling you the actual numbers of atoms. So glucose truly has 6 carbons, 12 hydrogens, and 6 oxygens. Hydrogen peroxide has 2 hydrogens and 2 oxygens in it. Propane has 3 carbons and 8 hydrogens. So the subscripts are telling you actual numbers of atoms. It's like the the real literal formula. When you come over here to empirical formulas, let me give you the empirical formulas of these three compounds. Because for every compound, you can write a molecular formula and an empirical formula. Let me see if you can discover what an empirical formula is. What I'm writing here are the empirical formulas for each of these compounds. And hopefully you see that it's essentially the reduced form of the formula. So for instance, with glucose, since these numbers are all divisible by 6, you go ahead and divide them all by 6 and you're going to get CH2O. Since these numbers are all divisible by 2, you divide them all by 2 and you get HO. And since this one doesn't really have like a greatest common multiple, it stays the same. Okay, so what is the point of an empirical formula? The point of an empirical formula is just to tell you, these tell you the ratio of atoms to each other. Empirical formulas are not getting at actual numbers. They're getting at what are the ratios. So for instance, there are 2 hydrogens for every 1 carbon. That's actually true. There are 2 hydrogens for every 1 carbon and for every 1 oxygen there. For hydrogen peroxide, the ratios are equal. You can see that they are equal. So empirical formulas are all just about ratios. So that's one thing that will show up on your test. Can you figure out an empirical formula from a molecular formula? It's just divide by the greatest common factor or whatever the word is. All right. How do you do combustion analysis? And then we're done. Like I said, it's a lab technique, which means there's going to be data that you're given. Let me do a practice question with you. All right, practice question. Upon combustion, that's burning in the presence of oxygen, a hydrocarbon produced 1.60 grams of CO2 and 0.819 grams of water. Find, or let me write determine. Determine its empirical formula. So the goal of combustion analysis is to figure out the empirical formula of the compound. So how I always start these is this. If it's a hydrocarbon, they always come in the form of C and H. So a C first, like CH4, C3H8. And really your goal here is to figure out what the subscripts are of the empirical formula. Now here's where you have to kind of learn just a little trick here. When you are looking at the subscripts of a formula, it is perfectly appropriate to say, okay, there's 2 hydrogen atoms and 1 oxygen atom, okay? However, it's also true that another way scientists think about this is that there's 2 moles of hydrogen atoms for every 1 mole of oxygen atoms. Now that might feel weird because we don't use the term mole in regular life, but remember with the word mole, if you can say it with the word dozen, you can say it with the word mole. Conceptually, the word dozen and mole are the same thing. You're talking about a grouping like large numbers of things by a multiplier. Dozen is 12 of something. Mole is 6.022 times 10 to the 23rd of something. So is it true that if you had water, you would have 2 dozen hydrogens every time you had 1 dozen oxygens? I think you think that that's true, and you'd be right. There would be 2 dozen hydrogens in a water sample for every 1 dozen oxygens. And if you can say it with dozen, you can say it with moles. So when you think about combustion analysis, think about, can we figure out the moles of carbon and can we figure out the moles of hydrogen? And that is going to be how we're going to approach this. We got to figure out that number. Okay, now how does this work here? Just a brief explanation of combustion analysis. You've got a furnace. You have fire burning, okay? You're burning stuff. You have your hydrocarbon, which contains carbon and hydrogen something. We don't know what the formulas are. And you obviously have oxygen in your furnace or else you wouldn't be able to burn it. So really there's a chemical reaction happening here between the hydrocarbon and the oxygen, just like every other combustion reaction. It's going to produce the same two molecules, CO2 and H2O, which, by the way, notice the word, produce this and that. That's what is produced in combustion reactions. Those are gases. They will be allowed to leave, and one will be collected in one place. I don't know if it matters which one is which, but this one will collect your CO2. It's probably got some kind of a compound in there that collects it or absorbs it. And this one will collect H2O. So that's really what happens with combustion analysis. You have this unknown material. You know it's a hydrocarbon, but you don't know what the empirical formula is. You burn it, you collect the CO2 gases. They're kind of moving along and they travel down here. And you collect your H2O gases and they'll be collected where they're collected. And then they weigh them. And that's where you get the data. Okay, so that's just generally how this works. So how do we deal with the data? I always just start with whatever one's written first. 1.60 grams of CO2. Don't ever, not follow who you're talking about. We are trying to figure out the moles of carbon. That's really our goal here. Oh, and I erased it, but did you notice that all of the carbon in the hydrocarbon, it all gets deposited into the CO2. That's kind of where it ends up. And frankly, all the H's in the hydrocarbon all shows up in the H2O. So that's why the CO2 is going to be used to help us figure out carbon, and the H2O is going to help us figure out hydrogen. So first thing is, let's figure out how many moles of CO2 is in this many grams. So we need the molar mass of CO2, which is 44.01 grams per mole. So that's going to convert to moles of CO2. And this is the one step that is maybe a little bit new, but hopefully you can see it's just logic. In every 1 mole of CO2, there would be 1 mole of C. Once again, if you can say it with dozen, you can say it with mole. If you had a dozen CO2 molecules, wouldn't you have a dozen carbons? Yes, you would. So that will get us the moles of C. So let's figure that out. 1.6 divided by 44.01. So with this one here, the caution is don't round too much. A lot of times people round too much. 0.036, I'm going to go 36. Don't do 0.04. You will actually cause yourself to get the questions wrong because the rounding error that you introduce will prevent you from seeing the answer. So make sure you don't round too much, and that would be moles of carbon. Let's go ahead and come over to the hydrogen, or the water. So you're going to do kind of 2 rows here. That's the grams of water. Let's find out how many moles of water that is. And now this part here is the one that people almost always mess up on, if they mess up. In every 1 mole of H2O, how many moles of H would there be? And it's going to be 2. Because think about it, in every dozen H2O molecules, you would have 2 dozen hydrogen atoms. Okay? So if you can say it with dozen, you can say it with mole. So let's figure out what this one would be. So 0.09092 moles of H. All right, so now that you have these numbers, we are ready to write them into our empirical formula. So C, and let's go ahead and write this. This is the moles. Remember how this represents the number of moles. And then H, 0.09092. Now, we're almost done. Clearly, empirical subscripts can never be decimals, okay? They have to be whole numbers. So the technique here is this. Always divide both of them by the smaller of the 2 numbers. What that's going to do is fix one of the numbers. It's going to at least correct one of them and make it a 1. So between these 2 numbers, this is the smaller number, 0.03636, 0.03636. So that ends up becoming C, and that's a 1, because this becomes a 1. And this becomes 2.5. Now, It's going to have a few more digits than that, okay, just depending on how many digits or how much you rounded. But what you're going to find is that at this step, they're either going to be both whole numbers. So depending on the question, if they're both whole numbers, you're done. If you get like CH3 or CH4 or C2H, well, I guess you wouldn't have a 2, C whatever. If you get a whole, if they're both whole numbers, you're done. You circle your answer, you finished. But the other possibility is that you're not going to get both whole numbers, but what you're going to see is that the other number is going to be the type of number that can be turned into a whole number very easily by multiplying by a 2, a 3, a 4, or a 5, really. I mean, for harder problems, it might be other numbers, but for you guys, it's going to be some kind of a floor, like 1.33 can easily be turned into a whole number by timesing it by 3. That would turn into 4. So you kind of have to have some, you know, sense of numbers or whatever. 1.25 can be turned into a whole number by timesing it by 4, because you can see like the 0.25, the 0.33, the 0.5. So what number will turn this into a whole number? What kind of multiplier? And hopefully you see it's a 2, but you've got to make sure you're multiplying both subscripts by 2. Remember, you're allowed to do this because empirical formulas are just ratios. So you can play with the numbers until they both become whole numbers. And this answer is C2H5. I will give you some practice problems on that. With this, you just have to have data that leads to a good practice problem. But that'll lead you through how to do combustion analysis. They're never any harder than that. So I knew it was going to be a long video, but we got through chapter 5. And thank you for your attention. Good luck studying.